Hello, everyone, and welcome back. Believe it or not, it has been about 4 months since I recorded the previous episode. I have a brand new computer, I have a new operating system, and everything, so I got to get back into the swing of things. The goal for this episode is to talk about a technique for calculating indefinite and definite integrals, which is called substitution. And this is going to be one of the most important methods that we learn in this class. And before we get started on that, there's one sort of subtopic that I need to talk about, which I will refer to as separating differentials. So suppose that I have a function, and I'm going to call the output variable for that function u and the input variable for that function x. And let's just suppose that I'm dealing with a function u of x, which is given by the formula x squared. Now, there are lots of different ways to denote the derivative of a function, but one way to represent the derivative of a function is to use a notation that looks a lot like a fraction, du over dx. The derivative of u with respect to x, which in this case would be the quantity 2x. This du over dx comes from the fact that the derivative is basically a little change in the output values divided by a little change in the input values. The only difference between this fraction and this fraction is the size of the delta x. Dx is just standing for a delta x that's very, very, very small. Now, if I think about the du and the dx as two separate quantities, then what I can do in this equation is I can sort of multiply both sides of this equation by a copy of dx. And I can clear the fractions in this equation and separate the dx from the du. And if I do that, this expression turns into du, a small change in u values, is equal to 2x times the small change in x values. This equation would be equivalent to what we've written up here, just with the du and the dx separated. Okay, so with that little aside taken care of, I have a thought exercise for you. When we're calculating indefinite integrals, when we're calculating definite integrals, the core of the process is finding an antiderivative for the function that you are integrating. Now, up to this point, our ability to integrate products has been pretty limited. The only products that we have been able to integrate are functions that have fallen into a special category where we could integrate the product using symmetry, for example, or we could simplify the product so that we could integrate it using the sum or the difference rule. But what if I was asked to find an antiderivative of a function like this one, which contains the product of 2x and e to the x squared? You may recall that if I wanted to find the derivative of the function e to the x squared, the derivative of a composition like that, using chain rule, would contain a product in the result. If I took the derivative of e to the x squared, the result of that calculation would be e to the x squared times the derivative of this upper function, the derivative of this function that has taken the place where x normally lives. So chain rule, the derivatives of functions that are calculated using chain rule sort of naturally produce outcomes that contain products inside. And what we're going to be doing today, method of substitution for finding antiderivatives, is basically chain rule in reverse. We are going to be looking at a product that probably came from applying chain rule to some function. And so we're going to be using chain rule backward to say that an antiderivative of something like 2x times e to the x squared is given by this original simpler function, in our case, e to the x squared. So let me explain to you what that process looks like in a situation that might be more complicated than this one. How, if you're integrating a product, do you know whether the method of substitution can be used? And then, in that situation, how do you actually use method of substitution to find the antiderivative? And to demonstrate those ideas, I'm going to use for an example this function right here. Someone asks me to find the indefinite integral of this product, x times cosine of 3x squared dx. I'm going to show you method of substitution with this running example. Now, the first thing I want to talk about is, faced with this kind of problem, how do I know that method of substitution is the method that I want to use here? Now, the major cue that I am looking for when I'm trying to decide, is method of substitution going to be viable? I'm looking for a product that is involving a function and a multiple of its derivative. To explain what I mean and how this is showing up in this running example, the first thing that I see in this running example is that there is a product happening. So here I have x times cosine of 3x squared. So that times, that product, is my first sort of cue that maybe method of substitution is necessary here. The second thing that I see in this expression that is pointing me toward method of substitution is that I see a function as well as a copy of its derivative. In this particular case, the function and its derivative that I'm seeing is the function 3x squared, who is present here, and its derivative is 6x. And what I have in my product is a multiple of 6x. I have 1/6 of this 6x here. If these two properties are satisfied, that's what I'm thinking I need to use method of substitution. So now that we've talked about how to know when method of substitution will be useful, let's break down step by step how to actually implement that method. So step number 1 of the method in general, when we were checking to see whether method of substitution would be viable, we were looking for an instance of a function and its derivative. So step number 1 is to set up a new output variable. And I will set u equal to the function whose derivative is present. So what does this mean in the context of our running example here? If I were going to look at this in the context of the running example, I would set u equal to the 3x squared showing up in this formula. I would set u equal to 3x squared because the derivative of 3x squared, 6x, a copy of that, a constant multiple, was also present in this product. So in this example, u is equal to 3x squared. Step number 2 is to rewrite the entire integral. And the goal is to replace every instance of x, the original input variable, with an equivalent in terms of u. So let me show you what I mean, once again, in the context of our running example. So in our running example, our original integral is integral of x times cosine of 3x squared dx. My goal is to go into this formula and rewrite it. And everywhere there was an x, I want to substitute and replace that x with something equivalent in terms of this u that I have defined above. So for example, since I have set u to be equal to 3x squared, if u is equal to 3x squared, then I would replace this 3x squared inside of the cosine with a single copy of u. 3x squared and u are equal, so one can be replaced by the other. I would also have to replace this dx in the expression with something equivalent in terms of u. And replacing the dx with something equivalent in terms of u, this is where I'm going to use the idea of separating the differentials, which I introduced upstairs here. To replace the dx in my integral with something equivalent in terms of u, the first thing that I'm going to do is take the derivative of u with respect to x. And that's going to cause a du and a dx to appear. So if u is equal to 3x squared, then du over dx would be equivalent to 6x, the derivative with respect to x of this expression. And if I separate those differentials, then I would be saying that du is equivalent to 6x dx. Now, if I were going to rewrite this a little bit to isolate the dx in this expression, then I would be saying 1 over 6x du is equal to dx. So I can use this expression to replace the dx in the integral with 1 over 6x du. Now let's go ahead and make those two substitutions that we've written down so far, this one here inside the cosine and this one here for the dx, and let's see what happens. X times what is now cosine of u, and then dx gets replaced by this new expression, 1 over 6x du. Behold what is happening in this integrand. By making this replacement, I have set up an expression where I have a multiplied x and a divided x. So that multiplied x and that divided x cancel out. And so having made those two substitutions of this u here and replacing this dx here in the back, I have now achieved an integral no longer has any x's in it, but only contains u's. Integral of 1 over 6 cosine of u du. Well, now this integral is entirely in terms of u. And this integral, rewritten in terms of u, is actually simple enough that we can calculate this antiderivative using just the standard antiderivative formulas that we learned earlier in the class. The antiderivative of cosine of u with respect to u is just equal to sine of u. Now, if method of substitution has gone correctly, it should always happen that the integral in terms of u is much simpler than the original integral, simple enough that you should be able to calculate it using just the standard integral formulas and properties. Integral in terms of u should be easy. Integrate normally. So in the context of our running example, the integral of 1/6 cosine of u with respect to u is just 1/6 sine of u plus c. To finish this problem, because we're almost done, to finish this problem, all we have to do is go back into this antiderivative, and everywhere we see a u, put back the original expression in terms of the original input variable. In this case, put back 3x squared in u's place. So step 4 is to put x back. So in our running example, we would be replacing that u in this antiderivative with that 3x squared that u is equivalent to in this problem. So we would have 1/6 sine of 3x squared plus c. And that would be the final answer that I would give to this problem. What is the indefinite integral of x times cosine of 3x squared? The indefinite integral is 1/6 sine of 3x squared plus c. And if you want to confirm that, you can always double check by using a regular ordinary derivative. If this answer is right, then the derivative of this answer should be equivalent to the integrand that I started with at the beginning of the problem. And I can double check that using chain rule. If I take this derivative, I'll get that 1/6 times the derivative of the inner function 6x times the derivative of the outer function cosine. The c will vanish. And once I simplify that, I get that x times cosine of 3x squared, which I had originally in my integrand. So this is the correct indefinite integral of the function that I started with. Method of substitution. Method of substitution is chain rule backward. Method of substitution is used to calculate the indefinite integral of certain products, specifically products where you are seeing a function as well as a constant multiple of that function's derivative. Okay, let's do a couple of more examples. I'll do one or maybe two more examples in this video. And then if you're looking for additional examples besides that, I will post a supplementary video containing many, many more examples of method of substitution. Okay, so let's go ahead and use the method of substitution to calculate this integral, cosine of x times sine of x quantity cubed. First of all, let us understand why method of substitution would be used in this situation. My first cue is that I'm taking the integral of a product of two quantities. The second cue is that this product is involving a function and a copy of that function's derivative. In this case, the function in question is sine of x, and the derivative of that function is cosine of x. So because I have both sine and cosine present in this product, that's a big sign that method of substitution would be used here. So in this case, I'm going to go ahead and set up a new variable u, and u will be equal to this function here, sine of x, that I have inside of this cubed quantity. Because now du dx will contain a copy of this cosine of x out here in the front. So du will be equivalent to cosine of x dx. In other words, dx will be equivalent to 1 over cosine du. What's nice about this setup is that if I go ahead and replace this sine of x cubed with u quantity cubed, and if I go ahead and replace this dx in the back with this expression I've just written down here, 1 over cosine du, then in this situation, I will have the integral of cosine of x times u to the power 3 times 1 over cosine x du. Once again, I get a cancellation happening with cosine and 1 over cosine. And as a result of that calculation, the integral that is now left contains only u's. And in addition to that, this is a very, very simple integral in terms of u. The integral of u cubed with respect to u is something that can be calculated simply using the power rule. And once I have calculated that integral using power rule, all I have to do is go back and replace that u with its equivalent expression in terms of x. One-fourth sine of x to the fourth power plus c. This function would be the integral of cosine times sine of x cubed dx. Note, it was possible to eliminate every copy of x and write the integral with only u. If this doesn't happen, if it is not possible to rewrite the entire integral in terms of only u's, no x's remaining at all, if this is not possible, the method of substitution will not work. Let me give you an example of an integral where I would not be able to use method of substitution to calculate that integral. For example, if I had the integral of x squared e to the x squared dx, this integral contains a product, but unlike the previous examples, it doesn't have this format of you have a function and then times the derivative of that function. I have an x squared, but I'm not seeing an x or a 2x or a 4x somewhere else in this problem. Instead, I'm seeing the function and another copy of that same function, x squared and as well x squared. Because of that, if you tried, for example, to set u equal to x squared to replace this guy up here and make it simpler, then du would be equivalent to 2x dx. So 1 over 2x du would be equivalent to dx. Now if I put that information back into this equation as we have it so far, let's see what happens. I have that u in the front getting changed. If x squared and u are equal, then that x squared in the front is equivalent to u. That x squared in the exponent can be changed, so I would have e to the power u. And if I change that dx, I would get 1 over 2x times du. So I was able to replace almost every x in the integral with something in terms of u instead, but the issue was that I sort of reintroduced another x in that process. So I was not able to eliminate absolutely every single copy of x from this expression, and if that happens, you are stuck. If you are able to use method of substitution, you are really looking for some kind of cancellation, like what happened here, or some kind of cancellation like what happened here, some kind of cancellation that helps you to eliminate all the x's in the expression at once so that you're left with an integral in terms of only u. So to finish this main video, all I'm going to do is show you how method of substitution can be used to calculate not only not only indefinite integrals, but also definite integrals. So for an example, someone says calculate the definite integral of x times e to the x squared dx from 0 to 3. Now there's very little difference at the beginning between this problem and the indefinite integrals that we've done so far. We're going to start by using substitution just as we did above to find a single antiderivative. And once we've found that antiderivative, we can find the indefinite integral using the fundamental theorem of calculus. All I have to do is plug the limits into the antiderivative and subtract. So working on step number 1, I recognize this as a substitution problem because I see two features of this integrand that are pointing me toward substitution. Feature number 1 is I'm seeing a product, x times e to the x squared. So that product is my first sign that substitution may be a method I need to use here. The second sign is that I'm seeing an instance of a function, and in the product, the derivative of that function. So in this case, I have the function x squared, and in the product, I am seeing x, which is very, very close to the 2x, which is the derivative of this exponent here. So I'm going to start out finding the antiderivative of x times e to the x squared dx using method of substitution, and specifically, I'm going to set u to be equal to this x squared, whose derivative is very closely related to this x that I have here in the front. If I do that, then dx would be equivalent to 1 over 2x du. Let's stick this information into our equation, and let's see if the result is something that is purely in terms of u and no x's remain. So I have the integral of e to the x squared is equivalent to e to the power u, and the dx in the back is equivalent to 1 over 2x du. Aha! Now I have a divided x, and this multiplied x in the front cancel out, and all that's left is this constant multiple, 1/2 e to the u du. And this is a very, very simple antiderivative for us to find. Integral of e to the u is just e to the u. So here is our indefinite integral, and 1/2 e to the u is one particular antiderivative that we can use. Now the last thing that I will do to finish up the antiderivative stage of this question is just put back in the place of u, to just put back the value in terms of x. So I'm just going to put back u equals x squared. So this is the indefinite integral, and right here is one particular antiderivative. Now that I've found the antiderivative and I've rewritten it back in terms of x, all that I have to do to finish this problem is go ahead and plug these limits of integration into the expression and subtract. So I would get 1/2 e to the 3 squared minus 1/2 e to the 0 squared. And from that, I get 1/2 e to the 9 minus 1/2 e to the 0, which is 1 unit. And this value would be the value of the definite integral in this question. I think the only thing to keep in mind when you're doing definite integrals using substitution is to remember that these values on the integral symbol, these are x values. So what you do not want to do, is you do not want to plug in u equals 3 or u equals 0 to this, right? Because 3 and 0 are not values of u. 3 and 0 are not values that should be taking the place of u. Instead, 3 and 0 are values of x, and they are values that need to be taking the place of x. Plug in x equals 3 and x equals 0. So that's the only added thing to keep in mind. doing definite integrals with substitution, just make sure that you're plugging in these x limits in x's place in your antiderivative. Okay, that concludes this video, and if you would like more examples of substitution, please go ahead and watch the supplemental video that I've recorded separately.